let me try to change our frame now and go to how to design a loudspeaker. For example, we were talking about at the beginning there was no computers. You must to make your models with still small parameters. I think that you must to solve the circuit and get the boat plot and something like else. Well, tell us about that early designing of loudspeakers. How was?
You know, a mathematical model is right as soon as you have sufficiently parameters to be a good representation of the reality. If you make a prototype, the profit of a prototype it is that it is a reality. So you don't know if your model is sufficiently precise. The prototype is the reality. But if, it is clear that in the beginning you had to do a lot of prototypes. But it's also a good solution. And if you found a method to reduce the number of prototypes, or because you have a good feeling, or because you have a good mathematical model, it is good. But the mathematical model is one method, but it is not the only method. In the beginning we had no till small system, etc., etc. I had made volumes with piston. We use it more to be able to make every volumes of air, every resonator systems like a mechano.
No, I mean, a model is only as accurate as the amount of detail you put into it.
Yeah,
and you never know the parameters. It's a bit like a weather forecast. You need an enormous amount of parameters to have it exact, and it's still not exact. Whereas a prototype is always a reality, and it's always exact. So at the beginning, you have to make a lot of prototypes, and then as the mathematical models evolved, you could do less and less prototypes. Prototypes, the only problem is they cost a lot of money to manufacture and time. So I think this is the idea: is that the more the more detailed your models get, and then it's always a combination of advancing with your model and then validating it with prototypes, and then you can move on with your model. And this was also very much the case with the AVA, where we had to move hand in hand between models and prototypes until we got to something that worked well. Yeah, and starting with little models with just pistons and things like that to much more complicated models.
Rigid pistons.
Yeah.
I had made air volumes which are cylinders, and you can change the volume with the piston in the cylinder, so you can get every volume you need. We use more this experiment system. But
it's like a compartment that you reduce the size, or
it's a prototype that you can vary dimensions. So instead of having just a sealed box, you'd have a tube with a piston that you can move, and you can change the volume of the box very easily.
Okay.
And an air sealed enjoined.
Yeah, with a sealed piston that you can pump up an air tube to make it completely airtight. So this allowed to test different volumes without making each time a new prototype or new cabinet.
And different port systems, all was prepared. But in the beginning it was more making prototypes and the right measurement system. So we can... I had always said that we make a loudspeaker to create sound a little like Bubka make the jumping. He needed to have a bar to know till where he make his jump.
Uh-huh.
Nureyev is an artist. He gives the impression to make big jumps, but he was a dancer. They need no bar to only the impression of the jump is important. For us, it is the reality of the sound, like Bubka, the bar. For us, the bar is the measurement microphone and the damping room, the anechoical room.
Mm-hmm.
That is our measurement system. And in the beginning, it was more important to be able to measure really the sound than to make the product, because you cannot improve your product if you can't measure it.
Yeah.
So in beginning, you must be able to measure, and after you can improve. And during perhaps 10 years of together improvement of the measurement make new products, and new products which are measured. We had to make also progress on the measurement systems, and after you know, so
this is
actually on the AVA there is a lot of new challenges in this domain.
Mm-hmm. And this is the classical philosophy about designing loudspeakers, using prototypes instead of modeling.
So after you have made good prototypes and good measurement, if you are able to modelize this prototype, you can make perhaps for a new model only one prototype. Then before, without model, you need perhaps 4, 5, 6 different prototypes. But the model is only a tool. The reality is the prototypes.
Yeah.
If you are not able to measure these prototypes, you can do every model that gives no sound.
And you have ever been working with that philosophy?
During the beginning, it was to maîtrise, comment on dit maîtriser, to master the reality, the prototypes. After, when Christian came, we were able to make the first big modelizing, because we were soon able to measure and to prototyping. And the modelizing was able to make more complicated things, but after you have to make the prototype and to control it. And so it must be sure that the modelizing is not only a pleasure for mathematical.
What is the?
Je sais pas, je me suis exprimé comme ça.
Oui, parfait.
Yeah. What is the most the hardest to design in a loudspeaker? What is the handicaps of a loudspeaker? What are the most problems?
The biggest problem it is that transducer, only the unit, is not able to give all the frequency response. Not like in an earphone. On an earphone, the transducer can give all the spectrum needed by the ear. Mm-hmm. On a loudspeaker, you need to have 2, 3, 4 ways to have all the spectrum. And the difficulty is to have a good homogeneity of these different ways in a loudspeaker. After that, you must think that the adaptive the adaptation of the loudspeaker in the environment, in the room, is also a big difficulty. So more the loudspeaker has a simple transfer function, easier it will be to integrate in the room environment.
With the acoustics.
Absolutely. I think it is also a big difficulty. By chance, we have only to make the loudspeaker, and we try to have the loudspeaker which is the most perfect, to be easy to integrate. If a loudspeaker has speciality, it's not a poor loudspeaker, but perhaps it is more difficult to integrate. Perhaps a bidirectional loudspeaker, like the electrostatic loudspeakers, are very difficult to integrate because the directivity.
Yeah, it is very narrow.
And you have the positive wave in the front and the negative
out of phase,
wave, which is reflected by
the
walls. It is a lot more difficult than if you have only one emission.
Mm-hmm. So you speak about 2, 3, or 4 ways, for example, for a loudspeaker. So you need filters to separate the spectrum. Mm-hmm. Every time you put a filter, you have different artifacts in the phase, Gibbs phenomenon, something like this. How do you solve that artifacts?
In the base, if you have no crossover, you have no risk of interferences. The interference makes a loudspeaker more complicated to integrate. But if you guarantee that there is no interferences on the crossover, on the crossover frequencies, I have to say, it is also a chance, because if you have 2 loudspeakers, you can control the directivity. Or with only one loudspeaker, you cannot control the directivity. You receive it, but you cannot control it. With 2 ways, when we have 2 loudspeakers, we can control the directivity if you control the phase between loudspeakers. So, if you are able to control the phase between loudspeaker, you can do a multi-way loudspeaker better than a unique way loudspeaker. Without controlling the phase, you are dependent of the hazard. If 2 loudspeakers are absolutely in phase, it is the same like a source of the same dimension than the 2 loudspeakers together. But you can know that the dimension can control the directivity of the system. So it is perhaps an advantage for the environment.
Okay, let's talk now about all-pass filters. They are filters that mainly maintain the magnitude but process the phase.
Yes,
okay,
that is the beginning of the all-pass filters. So you can change the phase without changing the magnitude. If a filter make phase rotation in low frequencies, perhaps at 1 kilohertz, you can, that is always a retard de phase,
Delay.
a phase delay. And the phase delay is corresponding always to a time delay. So, if it is at 1 kilohertz, it is the tenth of 10 kilohertz. So you have to change the phase, the time, the same on 10 kilohertz than on 1 kilohertz. So you have to make 10 times more at 10 kilohertz, 10 times more in phase than in delay of the time.
So you must
C'est
to
difficile de dire en anglais. Parce que ça fait 10 fois plus parce qu'on dit 10 times. Mais
Non, c'est juste.
Ouais.
you must to retard one of the ways respect the other.
Absolutely. Every phase must be respected. But respected is also perhaps to have a little advance to simulate a spherical response,
Yeah.
or to have a little delay, to have concentric to control the directivity. It's not only every together. The most simple is in a two-way. You cannot make a like a sphere with three, but here you have to have absolutely simultaneosity.
Radiation. Simultaneous radiation.
Yes, absolutely.
Okay.
Two ways or three ways.
And that is achieved with all pass filters.
All pass filters. Normally, you have always big phase rotation in a crossover.
No crossover.
Like you spoken about the problem in the crossover. With all pass filters, you need a lot of all pass filters. But so you have no more this global rotation. This global rotation is transformed in time delay.
Yeah.
But the time delay can be very little, so it is a big advantage because you have no more interferences, and you have a little delay, which is approximatively like 30 till 50 centimeters.
Mm. So, to make a concentrate idea as an end, we can say that the crossover filters introduce phase rotation.
So absolutely.
Yeah, the rotation in the slope of the filter, I think.
Mm-hmm.
The more slope, the more rotation. So that rotation introduce a time delay in the signal.
Absolutely, and we have to align all these time delays.
You must to put the all pass filters to synchronize
Yes,
the both ways.
And a big chance of an all-pass filter, it is that once you have made the calculation of the filter, if you change the calibration, that's no more a changement on the phase, you have a changement on the response.
Mm-hmm.
So you can change the response of an all-pass filter without changing the phase.
Yeah.
It is a big advantage. So you, on a loudspeaker with all-pass filters, you can make fine tuning without changing the phase.
Mm-hmm. This is the other side. The
La
other side of the
réciprocité.
hand.
La réciprocité. Yes,
Yeah.
absolutely.
Yeah, and
And
the
it was for us a big advantage because we could make calibration of our loudspeaker in the end.
just touching the all pass filters.
The global tuning was possible, so you can have a very good accurate of the loudspeaker, a very good similarity.
Yeah, in phase both ways,
Mhm.
and to propagate in phase.
Absolutely.
So
And very little difference between loudspeakers. It was, in multi-channel professional system, you need to have very good similarity of different loudspeakers.
Mhm.
And with this system, it was possible to do it because a normal loudspeaker have a precision of approximately the best 1 dB, normally 2 dBs. It is a lot. So we can calibrate to have the minimum of difference between the different loudspeakers.
But is PSA the only brand that use all pass filters?
It is absolutely our specialty, yes.
Uh-huh. How do you discover that problem with the faces?
Big discussions with Monsieur Zwicky. Yes, to discuss with people who have a lot of the creativity comes from échange of ideas between Monsieur Zwicky and I, Christian and Roger and I. So we can be creative because we have to always to justify our solutions.
Mm-hmm. And when you have
That's absolutely brainstorming.
yeah, and when you have more ways, it is more difficult to adjust all the faces.
I haven't really understood the question.
Yeah, when you have more ways in the loudspeaker,
Yes.
is it more difficult to adjust the phase of every way?
More ways and lower are the frequency, more it is difficult because if you begin at 1 kilohertz, you have to control it till 20 times, 1 kilohertz to 20 kilohertz. If you begin at 500 hertz, you have to control on 40 times.
Yeah.
Lower the frequency, and more ways you have, more complex. Before the computers, a man needed perhaps 10 minutes to make one filter with one pole. Perhaps he needed 1 hour with 2 poles. He needed 1 day for 3 poles. 4 poles was soon an approximation, a successive
Rotation.
Une approximation successive. In an all-pass filter of this model, 25 of this model, there is 64 poles.
64.
Yes.
How many capacitors?
2 capacitors for 4 poles.
2 capacitors for 4 poles.
Yes.
Okay.
All these capacitors are selected to ±1%.
Yes.
That's difficult here. And you know, it is impossible to make that without modeling. That is more than one life of work.
Yeah, really? You don't use
It is impossible.
and the body plot? You don't use the body plot?
That goes for till 8 poles. It is really in the beginning, our computer, which was the 386DX, worked 2 hours to make the transfer function.
Really?
And after that, we changed a capacitor, and we waited once again 2 hours after we changed two capacitors.
And it was fabulous because it was quicker than doing it by hand.
Yeah, I remember.
We were happy with that.
I remember when I was in my university, I made the body plot with my hand, not with computers.
Yeah.
So you imagine if there is 2 hours for one transfer function and to found the iteration for every component. One life is not enough without a computer, it's clear.
And what other innovation have the active PC audio monitors? I see that there is some feedback loop, a negative feedback loop that maybe controls the output impedance
Absolutely.
of the amplifier. Could you explain us a little bit?
Yes, you have explained right.
I prefer that it is explained
Yes,
by you.
it is a loop, but you can use this loop to control the velocity of the movement of the
Membrane.
voice coil.
Yeah.
Of the voice coil in reality, and control you have, so you can obtain a constant velocity. That is the maximum of damping. The results was not very satisfying because the velocity was perfect in low frequency, and in high frequency where the feedback was no more enough. Unfortunately, the damping was lower. So our idea was to use that not for controlling the velocity, but to have a constant damping. To obtain a constant damping on a loudspeaker, you have the fundamental resonance of a loudspeaker, which is the mass and the compliance. That is one fundamental resonance system. And you have the harmonics of the diaphragm, which is not the total mass and the total compliance. It is the partial mass of the membrane, which is where the membrane is no more absolutely rigid.
Yeah, it's
Yes, and the partial also compliance coming from the rigidity of the diaphragm. It is absolutely not the same mechanical functionment. So you have to have an output impedance different in the high frequency than in the low frequency. So on the loop, when you've spoken about a loop, you have to put a filter to have to differentiate the different domain
To compensate.
frequency compensate, and that was our ROE.
The inverse transfer function.
That not that is a constant damping. The transfer function is more the idea that it is always the same transfer function, and you have to make the inverse transfer function. That is more the idea of the all-pass filters, which are making the inverse function.
And with such system of controlling the movement of the membrane, you can stop the membrane when there is no sound and not oscillate.
Yes, it is. You can. The damping gives you the time for stopping the membrane. But if the time, it is easy to obtain a very short time in the middle frequencies, but it is difficult to have the same short time in the very high frequency and the very low frequency. So if we want to reproduce music, we don't want that one range is better than the other ranges. So it was more important to use this damping system, this loop, to obtain a constant constant damping. So the output impedance of the amplifier must be higher in the high frequency, lower in the medium frequency, and once again higher in the extreme low frequency, depending about of the parameters of the loudspeaker of the transducer.
And with such system, you control the impulse response of the loudspeaker.
The impulse response is the finality of the controlling, but you know, the impulse response has a very little energy, so it is difficult to measure an impulse response because more short is the impulse, more little is the energy. So it is better to measure on noise than on and by chance for us fonction de Fourier, the Fourier FFT function gives the
inverse.
La corrélation.
Yeah. And about the bass reflex, have you ever designed a totally sealed
Yes.
box?
Yes, it is the most simple solution. It is a sealed box. We speak about a reflex. It is an era of language. We had to speak about anti-resonant loudspeaker. A reflex system is one mechanical mass and one mechanical suspension, and the acoustic system is acoustic suspension and an acoustic mass, which is the port.
It's like a Helmholtz.
A Helmholtz, yeah.
A Helmholtz.
If this Helmholtz system is good calibrated, it is absolutely the energy acoustic is the mechanical energy is taken by the acoustic system.
Yeah, and
So
it is
you
in
have
phase with the radiation of the woofer.
the phase of the port is always absolutely coherent with the woofer above the Helmholtz frequency.
Mm-hmm.
Under, you have the end
It's out of phase.
it is progressively most out of phase. Where there is no more emission, there is the maximum of phase error.
When you have sealed boxes,
You have to have approximately 3 times more surface and 3 times more volume
yeah,
to have something approximately comparable.
yeah. But when you have a sealed box, when you excite with an impulse, and you see the time, the amplitude time graphic, you see that the impulse is short, and then the ripple is very little. But when you have a bass reflex, you see that the response is the impulse is the impulse, and then there is something resonating for the bass reflex port.
Not like that. If the damping is not well made, you obtain that. But if the damping is well made, you obtain that.
Even with a bass reflex port?
Yes, but the time is longer because you have the phase error of the system. But that is only a time problem, not an amplitude problem. Every high-pass system has a phase rotation.
Uh-huh.
And if it is a good high-pass system, you have no overshoot. But there is always an overshoot also because no overshoot will be possible with no mass. So I only say that in a reflex system, in anti-resonant system, you have the profit to have a better damping of the system because your acoustic system is absolutely the reverse of the mechanical system. You have a chance more to have a good damping, but you have always 2 poles more on your filter. So if you have 2 poles more, you have also more time.
Yeah, and more rotation. Did you ever try to put something to get more resistive in the bass port and see what happens?
It is better to damp the volume than the port, because the port, if you make a damping of the port, you have the flow of the air which makes noise. It is the same if you damp the volume, but without the noise of the airflow. In this one, you have acoustic resistance in the volume to control.
So the bass port.
The bass port, yeah. I think it is difficult to change to work on the resistance in the port, because in the port the velocity of the air is big, so you have always noise problems.
Yes, yes, because when you use a Helmholtz resonator for acoustics, you put just the resistive in front of the holes because the airflow is the maximum velocity.
Yes, it is easy, but the result gives noise.
Yes, yes, yes.
It is better to work on the air volume, to damp the volume, than to damp the port.
And about the electronics of the amplifiers, of every way of the loudspeakers, I see that the tweeter is an AB class and
Yes.
the woofer is a G class.
Yes, not the D, G.
G, G, G.
G, yes,
G.
not D.
No. What could you say as about the G class? Why do you choose it?
It was a very interesting system because more different voltage you have, higher can be the efficiency. So lower is the dissipation.
Mm-hmm.
If you choose 4 different voltage, plus voltage, plus half of the voltage, 0 voltage, plus the half, minus
The minus plus half.
and
Minus half.
total, and minus total. That is 4 different voltage. At half of the power, you have theoretically on square signal you can have 100% efficiency.
Mm-hmm.
So no dissipation with square signal. To be
Yeah.
clear. So you see that normally it is on an amplifier on the maximum that you have this characteristic to have the maximum of efficiency. It is on of the maximum power.
Mm-hmm.
On a G class, you can have this maximum of efficiency where you want.
Mm-hmm.
It is to the manufacturer to dimension his system to have the maximum efficiency where it is the maximum useful loudspeaker. So it is approximately on the half of the voltage.
Mm-hmm.
If you have the minimum of dissipation on the half, you shall have less less power.
Mm-hmm.
And if you have more power than the half of the voltage, it is only during the time of the
Of the
limiter
signal.
response,
Yeah.
of the peak. So you can, with an absolutely elegant analogical system, have a very high efficiency, so very little dissipation, because you know that it is not a good solution to have fan in a loudspeaker.
No, it's not a good solution. When you design the loudspeakers, the box, the size of the box correspond with the membrane size. Why not to manufacture big boxes even the woofer is little? Big boxes sound better.
Yes, it is easier to have bigger boxes, but the people need a lot of loudspeaker to have multi-channel, so the encombrement, the volume of the total installation become big, and for the work it is a problem.
Yeah, but if, for example, if I have only a pair of loudspeakers, even the woofer is this size, you can manufacture a very, very big. Mm-hmm. It will have a very good bass response.
It is a compromise. For a professional system, it is necessary to have the maximum of performance regarding the volume versus the volume, because it must be easy to transport, to control, for everything. So a little volume is a big advantage for professional. For mastering, the volume is a little less important, so such a volume is absolutely agreeable. And for hi-fi mastering, where the volume is not an advantage,
mm-hmm.
It is perhaps better to make more bigger. For me, it is absolutely clear that we have to make the best for a given volume, because the volume is it is what we pay in place or in money.
Mm-hmm.
So with this place, we have to give the best.
Mm-hmm.
So if you have a very little transducer in a given volume, the exploitation of this volume is a lot worse than with a bigger loudspeaker. With a too big loudspeaker, it is clear that there is no more movement, possible movement.
Yeah.
It is always a compromise. And you know, from the beginning of my work, and actually for a given volume, we can give 3 times more sound pressure level with the same distortion than in the beginning.
Oh.
So for the same performances, we can make the same result in 3 times less volume.
Mm-hmm.
Also.
And
that's one life of work.
And about the porous material that you put inside the loudspeaker, the resistive material.
Yes.
You put a lot of material to damp all the resonances and the movement of the air.
We have 2 materials, glass wool and polyester wool. The glass wool has an alpha Sabin of approximately 1. The polyester have an alpha 0.3, and you can put, if you want a big absorption, you need to put the material in the center of the volume, but it is not easy to have something in the center which is not rigid.
Yeah.
It will
vibrate
with the volume. So you have better to have less damping, but more material. and with both material you can adjust it. You can have a little of wool, of glass wool, a lot of polyester, or the contrary. And it is a game between these two materials, so you can damp the region of the volume you want.
So
This one is only with glass wool because that is a very little volume. There is not a lot of possibilities. In this one, that is a funny mix.
Right now my last questions. Which are the differences when you made a loudspeaker for studios and a loudspeaker for home studio?
For different in home studio and studio, professional studios. A professional, unfortunately for us, we are obliged to think only to professional studios, because we are in Switzerland and our production costs are justified only when it is the maximum of technology. And in home studios, they need a good standard, and if they have the possibility to improve the system, they can also use professional system, a little like a pilot of cars. He can make rallies with a car for everybody, but if he want to earn the rally of the World Championship, they buy the same but made specially for professional drivers. The difference between both are principally the top of the technology. You know, it is impossible to put a Class G loudspeaker, all pass filters and all that in home studio systems. But I think that in a studio, the loudspeaker is a little like the measurement system in a laboratory, which is the most important thing. They, after having made all the system, perhaps it is the first normal improvement to double perhaps the budget on the monitoring, so they improve really the reproduction. It is not the same for the other thing in the home studio. If they double the budget on the computer, the result will not be the double.
And my last question is all the elements that belongs a loudspeaker, which is the most difficult to trade with, to model, to expect the results you think, which is the most difficult element?
Je pense que c'est la continuité, comment faut dire,
La continuité de quoi?
la fabrication. To have always the same result.
Stability in production.
Yeah,
Also
to match all the loudspeakers.
Yeah.
Yes.
Yeah, but in terms of elements, of components, the less linear, the less predictable. The more handicaps that gives.
The biggest handicaps of a loudspeaker, it is
L'élément qui est le plus difficile à maîtriser, ou qui a le plus de variations.
Je pense que c'est quand même le traducteur.
Ça doit être le traducteur.
Ça doit être le traducteur, ouais.
Los traductores de traducción.
That's why we make ourselves the Twitter, because it was very difficult to have the good liability and good stability of production, and now we work a lot of the medium, and well, I think it is the transducer which is the most difficult too.
Okay.
But what is the most difficult? Is it more difficult to be the president of the country, or to be the best worker, balayeur des rues? To be the best, it is always the most difficult.
Yeah.
And so we have to make our best on all domain. You know, we have the chance to work in a multi-domain that is acoustic, mechanics, electronics, and we have to give our best on all domain. If it is easy, it is perhaps because we can do better.
Yeah.
If something is easy to do, we can do better.
What do you think will be the future of loudspeakers, or what do you expect in a future for loudspeakers?
I think that we can continue on the actual way, because if we are able to make loudspeaker where the directivity is more controlled, if the phase is more controlled, if the damping is more controlled, and if the dynamics is bigger, we can continue in this way. There is not a lot of possibility to make a lot better in volume, dynamic, but I think in directivity, in damping, in continuité de fabrication, there is more possibilities. And during a long time, the integration in the room was a really big problem. Now with the AVA, it is also a loudspeaker, an anti-loudspeaker. We can control a little the integration. It is a big improvement.
Well, I think
and we have to do always better in this way.
I think that we have a lot of information, and the interview was great for me. Thank you very much, Alain.
Thank you for your question, which was. I hear that you are that this is also your passion, because your questions were very pointu.
Very sharp, very to the point.
And for me, it was not always easy to answer.
No problem.
That's why perhaps I must do better.
No problem. We enjoy.